Hello and welcome to Programming Like It's 1979, from NAND to Tetris. This is it. Today we're going to start the last hardware project in the course and build a computer. If you've just come across this video and haven't seen the others in the series, you might want to start at the beginning and join us on our journey. Your mission, should you decide to accept it, is to build in HDR code the computer's memory, the CPU, and then connect the memory, the CPU, and the provided instruction memory into a computer. All of the files you'll need for this assignment are in the Projects 05 directory of your NAND to Tetris course materials. Let's go over what each of those means. Here's a schematic showing the basic layout of our computer's memory. The new concept we're introducing here is that of a memory map. Memory mapping is a way of accessing devices by tying their behavior to specific locations in memory. For example, in our diagram, we say that the keyboard has been memory mapped to location 24576. In hexadecimal, that's 0x6000. This means that if I want to read a key from the keyboard, rather than accessing some keyboard-specific function, I can just read the value in memory location hex 6000, and it will contain the code for the key being pressed. Writing a value to that memory location in this particular machine is meaningless. Likewise, I can read or write to the screen by reading the values between memory locations 16384 or 24575. When we write our operating system later, this is going to be a key part of how our graphics routines work. When implementing the memory module, the question you should be asking yourself is, how can you route the input and output to different devices based solely on the number representing the address? You've already implemented this several times, but you may not have recognized that that's what you were doing. That's the key to this exercise. Next, the CPU. This is what's going to take you the most amount of time. Here's a very abstract schematic of the CPU. This shows you its inputs and its outputs, but not what the inside looks like. The full spec is in the book, and you should read it carefully. But here's the brief rundown. On the input side, IN_M contains the contents of the piece of memory which is indexed by the current value of the A register in the CPU. Depending on the state of the CPU, this might be ignored. Instruction contains the instruction the CPU is about to execute. The reset input signals whether to restart the current program. In other words, to reset the program counter to 0. In terms of our outputs, if write_m is 1, then we will write the contents of out_m into the memory location address_m. PC indicates what the next value of the program counter should be. Okay, you might be saying, so those are the interfaces, but what's actually inside the box? Figure 5.9 in the Elements of Computing Systems gives you a partial block diagram with one proposed implementation. Conceptually, we can divide the work of the CPU into 3 rough tasks: instruction decoding, executing the instructions, and deciding what instruction to fetch next. You could work on these in any order you like, but when I do the lab, I'm probably going to place the ALU and registers first, and then grow the necessary bits on the decoding and instruction fetching ends out from the middle. I find that having the destinations for the control bits in place helps me understand how I should be decoding them. Last and least, you'll write the top-level HDL for the computer. You're going to wire together the CPU, the RAM memory, and the instruction ROM, and you'll wire up the computer's reset button appropriately. After the challenge of the CPU, this will be simple. To test your CPU, you'll want to load your computer.hdl file, once it's completed, into the hardware simulator and run the test scripts that run the add, max, and rect programs on it. If you encounter bugs, you may have to start disassembling code by hand. If you end up in that spot, my previous video, Machine Language the Hard Way, will be very useful to you. If you've stayed with the course this far, you've worked long and hard to get to this point. Have fun working on the project, and I'll see you in around a week or so to go over it in detail in our lab. Good luck!